In 1.5, we have one more topic that we want to discuss, which is how does substitution interact with the definite integral? So far that everything we have been doing has involved just finding antiderivatives, so finding indefinite integrals, but we want to do something that talks a little bit about how to deal with this definite integral where we're actually trying to get some kind of number out in the end. So this is going to work maybe in a pretty reasonable way. It's not going to be terribly complicated for us. So maybe we want to think about what's going on here. So our goal when we're computing this definite integral is to find an antiderivative as step 1, and then evaluate at these endpoints as step 2, according to our fundamental theorem of calculus. So in finding an antiderivative, we can still just as easily use substitution. That was exactly what we've used it for so far, so we can continue to use it. So let's see what happens as we use substitution here. Again, there's a question of what should we pick for u. In this case, something that I'm going to recognize here is that maybe something that's making this integral hard is this square root. And underneath the square root, however, I have this x squared plus 8x, and the derivative of that x squared plus 8x is twice x plus 4. It's 2x plus 8. So that relationship should give me some indication that a good choice for u here would be exactly what's under that radical, x squared plus 8x. And I know how to integrate the square root of u, because that's u to the 1/2 power, so that should end up working out. Again, this is something where I can recognize what a good choice for you is because I've done this process a lot. For the moment, you should be probably making a couple different choices for you at the beginning of a problem before you find the right one. So expect it to take a couple more times for you when you're working on this, just because you haven't had as much practice at it. So in this case, du over dx is 2x plus 8. Telling me that du is 2x plus 8 dx. And when I write this here, I mean that there are implied parentheses around this 2x plus 8. Just like there are when we're doing this integral, there are kind of implied parentheses around the integrand. We often don't write them just to simplify some of the writing, but they're implied to be there. So here, if I divide both sides by 2, I get du over 2 equals x plus 4 dx. And so I can replace the x plus 4 dx in the integrand with du over 2. So let's go ahead and do that. So I have du over 2 replacing my x plus 4 dx. U is going to replace x squared plus 8x. So I have square root of u here. And my limits of integration are going to remain as x equals 0 and x equals 1. It's important to remember that 0 and 1 here represent x values, not u values. We'll have another way of doing this problem here in a moment that allows us to figure out some u values, but for the time being, we're just going to leave our x values as x values, and we're going to write x equals to remind ourselves that they're x values. So let's see. So let's simplify this integral a little bit. We have 1/2 times the integral from x equals 0 to x equals 1 of, we want to think about the square root of u in terms of powers. So we want to think about that as u to the 1/2 du. And now I can apply my normal power rule to compute this integral. So this is equal to 1/2 times, we want to increase the exponent by 1. So 1/2 plus 1 is 3/2, and we want to divide by the new exponent, so divide by that 3/2, and we want to evaluate again from x equals 1 to x equals 0 to x equals 1. So simplifying things a little bit, I know that dividing by 3/2 is the same as multiplying by 2/3, which is going to cancel the 2, so I'll be left with a 1/3 u to the 3/2 evaluated from x equals 0 to x equals 1. In order to actually do the computation, I want to go back and replace u by its expression in terms of x. So 1/3 times x squared plus 8x to the 3/2 power evaluated now from x equals 0 to x equals 1. Finally, I can actually do this substitution now that I have my antiderivative here in terms of x. So I can replace x by 1. So that's going to look like 1/2 times 1 plus 8 to the 3/2 power. And I want to subtract away the expression evaluated at x equals 0. Fortunately for this problem, if I plug in x equals 0, I get 0 for both of these terms, and everything works out to be 0. So that's fairly simple. And actually getting a number out in the end here, let's see, this is 1/2 times 9 to the 3/2. Well, 9 to the 1/2 is 3. 3 cubed is 27. So this is 27 over 2. And now for the kind of second way of doing this. So we can start with our integral here from 0 to 1 of x plus 4 root x cubed plus, or x squared, plus 8x dx. We can go through the usual u substitution procedure. So the last time what we did was we got to this point after a little bit of work where we had this expression 1/3 u to the 3/2 evaluated from x equals 0 to x equals 1. And this time, instead of changing the antiderivative back in terms of x, I'm going to change these bounds of integration here in terms of u. So in order to do that, I'm going to think about the fact that I have this u here equal to x squared plus 8x. And that's going to tell me that when x equals 1, or let's start with x equals 0, when x equals 0, I'm thinking about u equals 0. And when x equals 1, I'm thinking about u being 9. So now what I can do is I can say, well, this is 1/3 u to the 3/2 evaluated from u equals 0 to u equals 9. I can plug in 9 for u, so that's going to give me 1/3 times 9 to the 3/2. I can plug in 0 for u, that's 1/3 0 to the 3/2. And I notice again this works out to be exactly the same 27 over 3. That's what we should have. Sorry about the mistake here. This 2 should be a 3. I just turned my 1/3 into 1/2 for some reason. So that's 1/3. This computation here is 27 over 3. And turns out that's even simpler. It's 9. So in the end, this area that we just computed using a u substitution turns out to be 9. And we can think about it in terms of finding an antiderivative in terms of x and using our original bounds, or we can simplify and find our antiderivative in terms of u and use u values as our bounds. Either approach works just fine. I personally don't have a preference. I think typically I'll probably end up going through this first approach because I find it a little bit more clear, and sometimes it's helpful to have this antiderivative in terms of the original variable around, but there's really not a good reason to choose one over the other all of the time.